Hello, everyone. I'm Iris Hui Zhang from National Taiwan University. So welcome everybody to attend the second virtual DL talk this year. And I'm currently the VP Activities of CEDA. And our distinguished lecturer today is Professor Theo. All right, so before starting the sales talk, please allow me just briefly introduce Professor Seo. Okay, so Professor Seo received his PhD degree in computer science and engineering from the Pennsylvania State University, and he is currently an associate professor and the department chair at the Department of Electrical and Computer Engineering at the University of Cyprus, and the director of research of the Chaos Research and Innovation Center of Excellence. His current research interests focus on embedded mobile and adaptive systems, tiny ML, embedded computer vision, and pattern recognition architectures and models, and intelligent system level monitoring and dynamic reconfiguration for performance, energy, and reliability of SoC. All right, so he has done a lot of works, and currently he serves as the associate editor for ACM's computing surveys, ACM transactions on emerging technologies for computing systems, IEEE transaction on computer-aided design, and IEEE's Design and Test magazine. And also, he served as a lot of major EDA conference committees, including 2025 date, and he served as the TPC chair there. All right, so I think he just elected as the IEEE CEDA Distinguished Lecturer for 2025 and 2026 period. So let's welcome our speaker. Thank you.
Thank you, Huiru. Thank you, everybody, for joining the lecture today. Following up to what Huiru said, my focus today is I'm going to try to convince you that it's actually good to be lazy. And lazy is not a bad thing. It's actually something that comes from the way our brains are wired. So it's not me saying that we are lazy, it's science. And the reason is because our brains are wired to make us consume the least amount of energy. And as a result, they give us essentially the motivation to move and do things only when the reward is high. And when the reward is high, we actually put the effort and we design and build new things, such as the remote control that helps us get up from the couch, not to have to get up from the couch actually and change the channels. Now, of course, we have AI nowadays, and everybody's using AI for painting, generating art, and writing. But then you have people complaining, which is I am on the same side with them, that I don't want AI to do my laundry. I mean, I don't want AI to do my paintings and my writing. I want AI to do the laundry and the dishes, so I can actually focus on do what I enjoy and what I like. Anyway, having said that, let's kind of move on to what we're going to talk about today. And what we'll talk about today is how to do something meaningfully and efficiently, because as Coach Wooden once said, do not mistake activity for achievement. And there is an old saying that a lot of people attribute to Bill Gates. I personally think it's probably dates much longer in time, that if you want to do a hard job, you must choose a lazy person to do that, because a lazy person will find an easy way to do it and do it efficiently. Now, why is this relevant? Well, because if you remember, based on the history of Archimedes, if you have the right tools, and we do have the right EDA tools, we can move the world, and we have managed to build a set of ecosystem, very innovative ecosystem that drives what we call today Edge AI, that spans from smart devices in our home, in our healthcare system, in our transportation and other smart societies as well. Now, why is that relevant to vision? Well, because vision sits at the cornerstone of, as a keystone of Edge AI. For those of you who are not familiar with the Gartner Technology Radar, this is the one from 2025, which places edge computer vision right in the middle, which means that it's a critical enabler, it's a productivity revolution, it offers a smart world, and it's also very close to what is very hot nowadays in terms of the technologies available. Now, if you also need further convincing that computer vision and embedded computer vision is in the heart of Edge AI, let me use biology. Our brains are actually wired in such a way that they fire up. The electrical activity in our brains happens when we open our eyes. And then 50% or more from our neural tissue is directly related to vision. And anecdotally, there was a study apparently that came out in 2015 that studied the biology of the brain for over the last 50 or so years, and they came to the conclusion that our olfactory cortex, the one responsible for the smell, is losing ground to the visual cortex. And this is evident when you go to a nice restaurant, you get a nice dish on your table, and the first thing you do instead of eating it is to take your mobile phone and photograph it because it pleases your brain. Now, obviously, the brain activity is what makes computer vision possible, not the sensor itself. I mean, it's our brain that analyzes what the sensor provides and makes context of what's important and why is it important. And of course, the brain is now used, the brain activity, I should say, is being implemented using what we have available today in terms of ASICs, in terms of GPUs, FPGAs, traditional processors, or any potential emerging devices such as quantum-based devices and so on and so on. And of course, the last decade, due to the insatiable need of AI, we have seen a tremendous boost in AI hardware, from TPU AI accelerators to Tenstorrent's revolutionary chips, NVIDIA's Blackwell, and so on. But we also agree that given the current state of AI right now, deep neural networks are dominating either convolutional neural networks or transformers. And we also understand that the size of these models, it's getting ridiculously large. And every time there is a new model being released, there is a much larger number of parameters compared to the previous one and so on. Now, just to give you an idea, modern transformers are in the order of billions in terms of their parameters. Even some older deep neural networks such as ResNet, they were within the order of millions of parameters. And even if this is not enough to convince you that these are not suitable for Edge AI devices, instead we need to design better models and better devices, there's also another issue that I want to emphasize, and I think this is probably the most worrisome, is that the International Energy Agency predicts that all AI workloads could consume up to 50%, up to 80% of all compute cycles, and this could accumulate to more than 10% of global electricity use by 2030, which is not too far. We're talking about 4 years from now. So, what do we do as designers and EDA practitioners? Well, we focus on designing better systems, better models, by optimizing them, by coming up with new computational ideas. We focus on building new architectures. We focus on building new circuits and taking advantage of new technologies such as memristive and analog processing units and so on. But at the same time, we also try to implement better optimization techniques such as pruning, knowledge distillation, low-rank factorization, quantization, and so on. And a lot of hardware-based techniques. For example, we change numerical representation. We follow approximate computing, post-Neumann architectures, and so on. Now, these all have one major disadvantage. They are all computational approaches. And what do I mean by that is that they are limited by whatever computing systems we can run them. They are limited by the mathematical boundaries, obviously, and they are limited by the available technology. Now, I want to take you back a little bit back in time, 30 plus years ago almost, when people were not able to build these huge models that we have today to solve the problem. Instead, they handcrafted neural networks, specifically what we called multi-layer perceptrons. And this is work done by Rowling Canada back in 1998. From the Carnegie Mellon Robotics Institute, where they handcrafted a multi-layer perceptron neural network to identify whether a picture contained a human face or not. And they actually handcrafted a second network to detect the angle of rotation for the face, along with some image processing techniques, to be able to identify also if a rotated face found in a picture was a human face or not. Now, we haven't done much different over the last 30 years when it comes to the way we build models. What we're trying to do is we take the sensor data and then we feed this sensor data to a neural network type of classifier. So if we have, for example, the particular example where you see a deer and a cat, and our task is to identify what's in the picture, as in there's a deer and there's a cat, what we do is we feed the information from the picture to a modern convolutional neural network, which tells us whether the object of interest is in the specific region, is a deer, is a cat, or it's simply background noise that we are not really interested. And to do that, we have to examine every possible location in the image. And if I go back again to how we used to handcraft classifiers, even if we have a modern classifier, the idea is that we need to examine all the data, and based on the detector, the classifier output, examine all possible search windows. And if we have to also account for the different size variations in the photo, in the image, for example, we had to downscale the image, generate more search windows until all of the possible data were examined by the detector. Now, to help you understand what this means, let's consider this scene. You see a nice street with some people in the background, some buildings, and so on. If I had to do this process over and over and over, what I would feed to the detector would be this mosaic, which is a lot of pictures, but none of these pictures really contains relevant information, except maybe a very small number that even if you're not familiar with how object detection works, let's say we're trying to find the people, there's only maybe 3 or 4 windows in this photo, search windows in this photo that contain people. And almost a decade ago, we started looking at this, thinking, why should we worry about examining every possible scenario? So we came up with the idea of using various filters that basically describe specific information events, such as motion or depth, which gives us the object size, or detection of multiple edges, which essentially translates into there's significant amount of information over there, and classify only what's necessary and what contains specific information that needs to be found in the image. And in fact, even when you run this cascade of filters in a very cluttered, in a very dense in terms of information scene, we discovered that maybe only 1% of the useful data actually need to reach the classifier. And this kind of motivated us for a few other approaches in doing this. Now, what do we do today? Let's say I'm tasked with solving a specific problem using a neural network model. The procedure we follow, as you're probably all familiar, is that we take the data, we take a foundation model, we train the foundation model with the new data, and we adapt it and optimize it to the specific task that we want it to do. Well, I'm arguing that this is not productive, and we're doing quite a lot. In fact, we're doing way more than this is necessary. If our aim is to design a model which performs good across all data and compare it with existing, let's say, benchmarks like ImageNet, CIFAR100, NIST, etc., well, sometimes this is too much. And to give you an idea, imagine if you're just trying to see whether there is a pedestrian in front of you in an autonomous car vision system, for example. Do you care if it's a male or a female? No. You just care if that person is there or not, and you take the appropriate action. So how do we lazy humans do it? Well, we use multimodal sensing, So if I hear a sound, I turn around and see something is happening. We use silencing, which is the ability to quickly differentiate what's important and what's not. We use our memory, both short and long-term spatial-temporal memory. We multitask, and we learn how to do certain tasks. So once we understand that needs this to be done, we set it and forget it. And we occasionally refresh our knowledge with any information that we had not acknowledged before, and so on, and so on, and so on. So in other words, we can be lazy in a very efficient, in a good way. We can do data-specific training. First of all, instead of taking a black box approach and building whatever data sets are there to prove that our model outperforms the state of the art, let's focus on what's important, what data is actually important to the task that we're trying to solve. You also have to remember that mathematical models will regress to whatever data points given, right? So do only what's necessary. Focus only when there is a high probability of something to happen, and use our short-term memory. Remember the principle of spatial-temporal locality in computer architecture and caches. Use that, and also do something very, very efficient that I will explain in a little bit. Stop when you have reached a relatively safe conclusion. Obviously, doing more work consumes more power, consumes more resources, and sometimes the application-dependent criteria do not ask for such a detailed, such a rigorous work. Now, how do nature or how do biological systems work? Well, they just do what absolutely needs to be done. So what I'm going to try and explain to you is that this is something that we also should try and focus. A lion, for example, sleeps. If the lion gets hungry, hunts and eats, then goes back to sleep. Now, enter dynamic deep neural networks. This is a term that I'm hoping most of you from the audience are more or less familiar. Just to give you a brief overview, the idea is that computation and energy reduction can be saved by adapting the model's depth or the model parameters to each corresponding input. If we reach a conclusion earlier, that means faster inference. If we adjust our operations to be aware from the resource constraints, that means better resource awareness. And of course, we preserve our full energy and our full capacity only when we need maximum accuracy for example, safety critical operations, and so on. Now, this is not something new. In fact, in machine learning community, this has been actually proposed for quite a few years now. Going back to 2019, there was a proposal for dynamically selecting some of the convolution parameters. And a year later, in 2020, there was another approach where an attention-like, transformer-like head could predict the convolution, the appropriate convolution kernels for a specific scene scenario. And some of the previous work that we also did involved using different convolution kernels versus a fixed convolution kernel, specifically a dilated convolution kernel similar to the one shown in the figure. And in fact, we had very encouraging results in terms of speed and accuracy compared to state of the art for scenarios for emergency response applications as well. So what I would like to talk about right now is focus on a case study on UAV-based vehicle detection, a very common problem that impacts both critical and non-critical applications, for example, traffic monitoring and so on. And I want you to take a look at the four photos that I'm showing you, because all of these have been taken. It's a photo of the same location, taken from 4 different altitudes, starting from the top left from 50 meters and going down to 400 meters in the bottom right. Now, obviously, you can see that the level of detail and the level of visibility in each of these photos differs greatly. Now, why am I saying that? Well, because if our problem was to discover or build a model that would classify and detect and count cars, then our standard approach would be to take a foundation model, train it with a large number of data of images that would be acquired from multiple, let's say, UAVs, then optimize that model for the edge, put it on an edge device, put it on the UAV, and start computing. Well, it turns out that this is probably not the best way to do it. So to prove that this could have been an overkill, what we did is we partitioned our data set into 4 different altitude groups. And for each altitude group, we experimented with a couple of parameters, specifically the input image resolution and the channel multiplier width of the convolution kernel. What we noticed is that for each altitude, the corresponding configuration, which gave the best accuracy, best performance, and best energy overall, was completely different. And just to give you a very brief overview, for low altitude, as would have been expected, the reduction of the computation process due to the fact that you have a good amount of information, we can reduce both the multiplier width and the image resolution quite a lot and still get very good accuracy. And you can see it all in the green boxes in the upper left rectangles. But of course, as you go up high, you need more resources, more multiplier width, and more resolution in order to be able to balance this. Now, the question is, do we need to do this for the entire number of image data we have, or could we do maybe a dynamic mechanism that adapts based on the altitude? So our very first approach was to build a very simple controller based on a very simple threshold examination algorithm, where depending on the altitude that the UAV was flying, the corresponding parameters, i.e. the resolution and current width, were loaded into the neural network pipeline, and the specific results were obtained. And we put that on a Jetson, on an NVIDIA Jetson processor on the UAV, and we ran some experiments, and we saw that even for a simple threshold mechanism, we have noticed not only a gain in memory power and latency that we anticipated, but we also gotten some better results in terms of the accuracy, because for the specific context that we were flying, these optimal parameters for the network were the ones that were giving the better overall accuracy. So the question now becomes, can we do better? Maybe use reinforcement learning as part of the mechanism? Can we use hardware, and namely FPGA-based partial reconfiguration, where the frequency of the context switch, the reconfiguration overheads, and any other ML-based models such as transformers could be one of the solutions? This is something that we are currently working on, and I think over in the next few months we will have much better results. Maybe in a future lecture I will be able to present them to everybody. Now, there's another also problem that we're dealing with when it comes to edge vision, and is that of the resolution. Now, most of you probably do not remember that cameras 30 plus years ago, the best resolution that you could afford was maybe 320 by 240, because nowadays there are cameras that give you 8K resolution and they still grow. Now, what does that mean? Well, it means that if I have to take that entire image and build a neural network, even a very simple convolutional neural network, to process that image, I will need an extremely large number of inputs, which translates to an extremely exponentially, I should say, a larger network than what we're seeing today. And just to give you an example, a typical YOLO today, I think the resolution, if I remember correctly, it's around 512 by 512 pixels as an input. What does that mean? It means that we either have to find a way to shrink the input images and feed them to the YOLO detector, for example, if we're using YOLO, or find a better and more creative way to do that. And we have been working a little bit on that a while ago, actually, where we followed what humans do. So if you are tasked to try and detect something that appears in, let's say, your viewpoint, you're not going to look in the entire viewpoint. You're just going to focus on where this activity happens. So what if we can partition the entire viewpoint in smaller tiles without changing the resolution, and then find an intelligent way to take those tiles and fit them to small and very fast convolutional neural networks, and somehow keep some memory that gives us a better overall result? Well, this is based on focusing on essentially on what humans do. So if you're trying to do a traditional scanning pipeline that I mentioned in the beginning, and you are looking at everything in the figure, and then you generate all possible scales and areas, this is just doing too much, and sometimes you do a lot more by doing less, as my example figure on the left shows. Instead, it's better to identify quickly, find an intelligent way to identify quickly what's important, and fit those pieces of information that are important completely unchanged, so you do not change the information that you give to your neural network, into your classifier, focus on having small, efficient, lightweight classifiers, and get some results. And to give you an idea, the results doing this implies that you have to have a mechanism where you examine selectively the tiles. Now, obviously, if we examine all the tiles, this is something that obviously we don't want to be doing that. Another way is to do a round-robin approach and basically scan and just process one tile at a time. This is on the other opposite side of things, so we're completely putting a priority that is based on which tile appears and where. But if we introduce some level of intelligence, that is, keep memory of what was found before and keep a memory of the amount of things that we found before, so selecting and focusing what's important, we actually can see that we can build a system that instead of having a very large and very complex neural network, we can have much smaller neural networks, much smaller convolutional mechanisms through a pool of neural networks, and based on the chosen tiles, proceed those much smaller and so on and so on. And of course, as I mentioned, you need the occasional refresh. So after a while, it's good to check back and see if something changed. And in that case, you can do only once a larger neural network, just like we do nowadays, and refresh our field of view to make sure that we haven't missed anything else. And this, I'm hoping everybody can see the video. This is actually a video from approximately 300 meters high from a UAV that shows a car detector and how well it performs given what we were targeting in the very beginning. Now, can this be improved? Well, yeah, we can find a better way or a little bit more appropriate way to dynamically choose and rank the tiles which are considered important. And this is something we're working right now. One of the things that we're looking right now is to rank these tiles based on saliency. Saliency is the human ability to detect what's important information and what's essentially background noise. And this can be computed via several ways. So we're trying to identify which is the best way to do that. And by ranking the tiles based on this, then able to build a small lightweight convolutional neural network that aggregates and gives us a final output. And of course, this builds on what I'm trying to argue all this time, that this gives us lower computation, better energy efficiency, faster inference, and focuses only on what's really necessary. So another thing that is inspired by human nature in laziness, if I can use the word to bring you back to the topic of the lecture, is how about shortening the path? And of course, the comic shows Pythagoras, who very famously invented the Pythagoras theorem that computes that the shortest path going from the one side of the rectangle to the other is not the horizontal lines, but the hypotenuse lines. Now, I'm going to take you again back in history, almost 20 plus years ago, where the state of the art in object detection was a detector called AdaBoost by Paul Viola and Michael Jones by Microsoft back then, where they proposed a cascaded set of feature examination algorithms, where each stage would examine a specific set of features based on what the level of detail, for example, and the area under examination, the image under examination, will be classified as a face or not, for example, only if it passes through the entire set of these cascade classifiers. We're talking about, in the specific implementation, 38 stages and 600 features, which is quite a lot. Now, all this is very similar to what we call today the principle of early exit deep neural networks. In other words, if we can place an exit branch between, let's say, convolutional blocks in convolutional neural networks, where we evaluate the intermediate feature maps that are being produced. Then if the branch is confident enough, we can stop the computation. Otherwise, we can continue, examine more the intermediate feature maps, examine, maybe the output of the next layer again, and so on, and so on, and so on. So the main implementation comes from the fact that if you have a major, like a main backbone, then instead of going through the entire set of layers, and usually this is quite a large number with the deep models that we have today, instead of having to do that, what you do is basically you place these exit branches. The architecture of the branch could be based on a convolutional layer, for example, optional batch normalization, ReLU activation, pooling, flattening, and so on and so on, along with a confidence estimator, usually a softmax approach. And if the confidence threshold is high enough, so let's say we put a cat and the confidence threshold in the third block says that I have a confidence of 95% that it's a cat, and every other class probability it's below 5%, then we can make a very confident decision and say, well, it's a cat, and stop right there and not have to go through the rest of the pipeline. Obviously, this implies low extra computation, very fast inference, good confidence calibration, and acceptable accuracy. Now, of course, this is not, okay, let's put it at 80%, for example, and forget it. It requires very careful design of the exit architecture. And this obviously comes with necessary design space exploration, because if we exit a lot with high accuracy, that is obviously what we want. But if we are exiting with low accuracy, or if we are not exiting because our accuracy, the confidence level is low, that means that we're basically doing more, but we're not exiting. So essentially, we are wasting our time. Now, from an ML standpoint, usually ML engineers have to deal with the strategy of where to place the exits, have to deal with exit criteria strategy, which is usually set by the confidence threshold, as well as the exit architecture, that is whether I want to have a convolutional layer, whether I have fully connected, pooling, batch normalization, and so on. Now, I want you to also take a look at this slide, because if you're looking at it from a machine learning point, from an ML engineer's point of view, you will see that if we exit, for example, if we place the exit head very early, obviously this implies that we may not have accumulated sufficient amount of information to make an informed decision early. So obviously it will be of lower accuracy and lower reliability when it comes to the confidence of the decision. And I want you to keep that in mind. But it will also be of lowest latency and highest energy savings, because it will exit very fast down the computation pipeline. As you progress down the depth, obviously things are reversed. So the deeper you go, the exit becomes more accurate because the confidence level rises, but you waste a lot of resources, and of course, your savings are not as usually or as should have been expected. Now, this is from an ML engineer standpoint, but most of us are hardware engineers and designers, and as you probably understand, the word reliability to us does not imply reliable accuracy. It implies reliable operation in the presence of faults. So if I change this and take you back into how this is translated and look at it from a hardware engineer's standpoint, you will see that if I exit too early, that means that I'm exposing my hardware and the software into a lesser number of time exposure, which reduces the vulnerability to, let's say, single event upsets, for example. Whereas the more deep I go, there is highest fault exposure, which obviously implies lesser reliability, and so on. Now, a very similar trend is also evident in the choice of the exit architecture. So if I have, for example, a fully connected, if I have a convolutional plus fully connected, I will have a better result, but with more resources. And the same translates to the reliability in terms of the machine learning point of view, but also the reliability in terms of the hardware point of view. And then very quickly, the same trend is also evident in detecting and setting the chosen threshold, the confidence threshold. If I set it too high, obviously I will have a lesser number of samples exiting. So that means I am doing the exit computation, but I don't have the visible benefits. On the other hand, if I lower it, I will have much less accuracy with a lot more energy because I will not be exiting, which means I will have to be going through the entire pipeline and so on. And this is also reflected in the reliability in terms of the hardware as well. However, I want to be on positive side and state that there are a lot of good things when it comes to early exits. If we build it correctly, then if it works based on what's planned, then there are a lot of benefits because we are saving a lot of effort, a lot of computational effort, a lot of energy, and of course we do things much faster, which is sometimes more important when it comes to real-time applications. On the other hand, if we're not having a bad design, having this implies that we spend a lot of time trying to build a system that not only doesn't work, it does a lot more than what we have anticipated it to do as well. Now, how to evaluate if something is good or something is bad? Well, in machine learning point of view, usually you check the accuracy, the model size, and the performance in terms of the latency. However, if we go back to how we design edge AI devices, and an often overlooked metric that I want to talk a little bit about is the concept of hardware-based reliability, the concept of having potentially hardware trojans and side channel attacks, the concept of computational complexity, coding issues, inference anomalies, and so on. And my focus is going to be mostly for the next few slides on hardware-based reliability, either due to soft errors or various other things, focusing at this particular set on transient faults and not permanent faults. Now, of course, one can argue why don't ML engineers care about this? Because they don't, not because they're not important, it's because that in their mind, if I say that the network does not operate correctly, that means that they haven't trained it sufficiently. So they need to go back and retrain the network, maybe using mechanisms such as dropout and so on, to make sure that they catch all the variability in the input data. But in HAI devices, the reliability does not come always from variety and variability in the input data. It also comes from the underlying hardware architecture and software that runs on this hardware. And in dynamic neural networks, all these parameters that I have just covered are extremely, extremely important. And every design decision impacts the performance metrics that, as we all very well know, in contradictory ways. So if I pull one direction to gain more performance, that means I sacrifice energy, I might sacrifice reliability, and this is not usually a linear relationship of these design choices. So what do I have? I have a huge design space in terms of the number of possible exit placements, architectures, thresholds, and so on. I have a lot of trade-offs that I need to consider that are usually contradictory, and I have a very costly and manual evaluation to determine whether a model that is being running on an edge AI device is reliable, is fast, is slow, is accurate, is large, is small, consumes X energy, and so on and so on. So if I go back to our fundamental embedded system design approaches, if you recall, we start by our constraints and objectives, which are very well known: latency, accuracy, energy, and so on and so on. We have our design space generator, so generate the candidates based on the placement, architecture, and strategy. We have the performance evaluator that we need to, verify what each possible architecture results in. We have our multi-objective optimization, similar to any embedded system optimization, search and optimize approach. And last but not least, we have the produced solutions, usually called Pareto optimal solutions, that are deployment ready, and they take into consideration the trade-offs involved as well as the assessed impact. Now, one of the problems that we had, and we tried to come up with a good solution, is to measure in a meaningful way the reliability of early exit neural networks. Now, in traditional reliability assessment techniques, usually this comes with fault injection, either at the hardware or the software level, where you inject faults for every fault model, for every type of operation, and you try to determine how vulnerable your system is. Well, in dynamic networks, this is not easy because you have not deterministic execution paths, you have uneven fault sensitivity, and you have complex and fragile control logic that controls all this dynamic data flow. And as a result, we are not able to quickly and with existing techniques go through and do some evaluation. So what we did as an initial approach with my colleagues and my students and our students is that we came up with a framework where we are able to place, we used a very simple inception convolutional neural network based on the GoogleNet inception model, where we experimented with various exit placement strategies, where we put the exit in the shallow layers of the network, then on the deep layers of the network, and we also experimented with two exits, one in the shallow layers and one in the deep layers. And what we did, we noticed is if you inject faults in these particular pipelines, obviously we expected to see a reduction of accuracy, but we also saw some other interesting observations that impact the fault campaign. And one of those is what we called non-materialized faults. Now, in a traditional approach, if you inject a fault that you expect it to hit in a specific hardware or in a specific computation stage in time, based on that, you extract a fault campaign and you determine how many faults and where you need to inject them so you can have a strong confidence. Now, let's consider a very possible scenario. You are targeting let's say the second set of neural network layers that is after the early exit one. Now, let's say, however, that your early exit one is actually taken, so your computation ends. So if you are planning to inject a fault in the layers beyond the early exit one, that means that that fault will never materialized. How does that impact? Well, we need to change our fault campaign. And by doing that, we actually also observed, besides what I just talked, we observed a few other interesting aspects where which validates some of the hypotheses that I presented earlier, that if your exit strategy works, then your reliability actually improves if you exit in the early stages. And this is so evident by the second set of critical faults that we observed in some of the experiments that we did on the inception framework. And this sometimes changes both any mitigation strategies as well as any other more detailed fault campaigns that need to take. Now, there's also another issue that I would like to raise here, and this is basically having to do with faults that do not necessarily impact the accuracy. Let's say we're feeding the classifier a cat. Let's say now that based on what it should have happened, let's say exit next to the convolutional block 2 would have been computed, the threshold would have been high enough, the exit would have been taken, and the prediction would be correct, i.e. a cat. What happens though if there is an SEU that corrupts an intermittent feature map, and then instead of exiting, you go back and take the entire pipeline with the correct prediction? Now, in comparison to any other fault evaluation approach, you would say that this particular fault had no impact on the computation, but it did have impact on the power consumption and also on the latency, because it caused the entire system to go through the pipeline without actually being necessary. And this is something that it was another observation from our early approaches. Now, how do we improve these things? Well, going back to our embedded system design 101, we build a solution, we evaluate the solution, we try to find what is the optimal system in terms of where we place the exits, where we place the strategies, and so on, and so on, and so on. Now, how does that work in dynamic deep neural networks? Well, or even early exit neural networks, same way it works for all other CNNs. And that is usually for techniques that we call neural architecture search, which I'm pretty sure most of you are familiar. Very quickly, neural architecture search uses key enablers such as differentiable NARs, reinforcement learning, evolutionary algorithms, Bayesian optimization, or other surrogate models for fast evaluation, and tries to produce a set of Pareto optimal neural architectures that are good in meeting the constraints and the objectives of the optimization problem. And while we were working on the reliability aspects that I mentioned earlier, we also built the framework which we call Armor, that we presented actually next week at ETS, in case any of you is there and you can come and talk to us and see and find out more about this, where it formulates the reliability within the neural architecture search framework, and is able to find Pareto optimal solutions for some popular networks such as MobileNet V2, ResNet 18, and ResNet 34 that take into consideration both the reliability and the performance, but also the accuracy trade-offs in terms of having multi-objective constraints satisfied as well. Now, for the last part of my talk, I'm going to also give you a couple of directions that come or are can be inspiring to you from this work, namely that, okay, we have a nice feel of what these dynamic networks do. If I go back to what I talked about in the very beginning, if you remember about having different channel widths or different multiplier widths, what if I have an exit branch that, based on the intermittent partially features, can determine whether I can shift to a smaller width for the next layers? What I have if I have a branch that can say, you know what, now I can use a lower resolution instead of having the high resolution output? What if I have a branch that says, you know what, instead of having the same convolution mask throughout the end-to-end pipeline, maybe choose a different, maybe dilated Atos convolution with a rate of 2 or with a rate of 4 and so on. Now, what about the training? In the majority of the cases in HAI, we deal with inference. Obviously, I'm not saying that it's easy to train large models on the devices, but if we focus on training or models which are actually better in terms of responding to these scenarios, we might be able to have better performance overall. And this is something that started as an effort with a couple of colleagues here in terms of using the forward algorithm proposed by Geoffrey Hinton a few years ago, where instead of using backpropagation, which, as you know, it's not biologically plausible, it's just a black box that works because we know it works due to gradient descent, instead of going and feeding, okay, here is a cat, the output is a cat, come back and change the weights, focus on what is a cat and what is not a cat, and give a score and train in a layer-wise approach using gradient descent only for a single layer. And this is a work done that appeared in the AAAI conference back in 2024, that basically its objective is to train neural networks on a layer-wise approach. So I'm not going to talk about that. However, I'm going to mention this because we also played a little bit around with early exits, and the results that we observed by putting some exits into these layers were extremely encouraging by actually achieving accuracy in the vehicle detection scenario mentioned earlier that is actually extremely comparable to the end-to-end accuracy, but with a significant reduction in the MAC operations, which reflects reduced energy consumption and also reduced latency. So to summarize and give time to everybody for possibly some questions and answers, I'm arguing that dynamicity is good, even though I called it laziness in a way in my introduction. If we look at certain things and dynamically decide whether they are good or bad, this can give us really good savings in terms of energy, power, performance, and so on. It can give us accuracy maintaining a safe operation, and it can also address issues stemming from reliability and robustness and so on. And of course, all these come with the associated challenges that our community is eagerly trying to address. We need, for example, EDA tools and CAD tools to address multi-objective optimization, placement, runtime policy, verification and validation, and so on. We need methodologies such as neural architecture search frameworks, accelerator mapping, and so on. And we also need to play around with the mechanisms at the model level collectively and not in a single dimension so that we can optimize both the energy and power, the performance, accuracy and safety, and the reliability. And remember, even though we are lazy, we have to also remember that trying to solve a very important problem, it's not about the solution itself, but it's also about enjoying what we do. And to quote Gaddafi, it's not the destination, it's also the trip, because we gain more experience. That means we can use that experience and continue to be lazy and only do when we have high motivation and high reward. And at this point, I would like to thank everybody, but particularly my colleagues here at the center, Professors Maria Mijail, Sergios Timoteo, and Christos Kirko, and of course, all of our students and colleagues from abroad that collaborated with us in putting this together. And I think, where if we have time, I think we can take some questions.
Yes, thank you. Thank you very much for the inspiring talk. So, any audience, any questions from the audience? Welcome to input your questions in the chat. All right. So, basically, there is one basic question from the audience that the test is asking whether the slides can be shared after the talk.
Yes, obviously. I will talk to Jackie and the CEDA administration, and yes, I can make them available.
Okay, thank you. And I think the audience is trying to input questions. So before they input their questions, maybe I can start from some simple questions first. Yeah. All right. So I like the idea of the being lazy very much. All right. So there are several interesting ideas proposed in your talk. So first of all, you mentioned that we can use dynamic neural network with various neural networks. Each of them can have different parameters and complexity and so on. So the questions, the first one is that if we handle multiple deep neural network for simply the same task to achieve the being lazy. So how about the hardware overhead? Do you have any experience for this?
So if I understand the question correct, basically instead of doing one exit at a time, parallelize the exits. Is that what you're asking me, Huiro?
Yeah. I'm asking that since you probably we probably have to construct several neural networks at the same time, and each of them can handle different maybe
Oh,
different
okay.
input. All right.
Okay, I
So
understand.
how about
So,
the hardware cost?
well, this is not something that we want to do, actually. I think the objective is to focus on minimizing the exit. I mean, this is very similar in going back in time and trying to, solve, for example, if you all recall the superscalar architecture. Superscalar architecture came out as a way to parallelize instructions. But after a point, the complexity of the superscalar approach was so high that the benefit, if you were trying to do something, was much smaller. So I think that there has to be a limit as to how much we can build in terms of each exit branch, for example. So if I'm going to have a very small lightweight exit branch that is gonna be implemented every, let's say, 10% of the time, and the remaining will be another exit branch that will be implemented like 50% of the time, that is much more complicated to design, then obviously this is not a good thing. So it's essentially a very good parallel to the Amdahl's law. So if our exit is utilized a lot and it's actually quite accurate, and if it's quite small, then it's good to, build that and maybe add a little bit of complexity to make it more accurate, provided, of course, that it's utilized a sufficient number of times. So let's say I built a network with 3 exits, and exit 1 is very simple and very small, but it's quite never utilized. Does it matter? If I build that exit, though, and it's very complicated, and it's utilized every 1%, and that 1% happens to be always correct, then maybe this is something that we can do, because every time I choose that path, it will be almost certainly an exit. So it comes to a balance between how frequently you use the exit, which is something that can be determined from the corresponding task or data set that you do, because you cannot really have an estimate on how frequently an exit is taken or not, unless you run a good amount of data to understand the behavior of the exit. If you have that, then it's easier and you are able to focus on optimizing or not that particular exit. So it's very similar to Amdahl's law. So if you have a unit that it's 10% overhead, as much as you optimize it, it will always be 10% overhead. So
Thank you. Yeah.
hopefully that was clear.
Yes, yes, thank you. And we got several questions from the audience.
Mhm.
So the first one is from Mikhail. Hope my pronunciation is all right. All right. So the question is that regarding the error tolerance of early-exit neural networks, if we inject errors, are some exits more error tolerant than other exits? For example, is the final exit more error tolerant than the first exit?
That is a very good question. We only have a few experimental approaches to validate this, so I cannot speak on a fully generic case. But in reality, if your exit in the beginning has the same architecture with the exit in the end, then if you exit in the beginning, that means that you are less vulnerable to soft errors in the latter stages, the latter layers, which makes the overall architecture in the latter layers, including the exits, less vulnerable. Now, if the architecture is different, though, and let's say the probability of an exit in the beginning and the probability of an exit in the end is more or less the same, just to hypothetically give you a scenario. If we exit on both, but the architecture of the second exit, of the last exit, is much more complicated, then obviously you will have more computations, more surface area, to use the circuit term, and that means more vulnerability and more exposure to soft errors. I think, though, there is not a specific answer in terms that this is better than the rest. I think it has to be taken into consideration, as I mentioned earlier, with the utilization of each exit. So if you're building a system that detects cars, and that particular system is exiting on the very few, let's say, layers very often, then obviously, and going back to Amdahl's law that I mentioned earlier, obviously that exit will be utilized quite a lot. So you can, and if you notice that through your vulnerability analysis is quite vulnerable, you can also make it more shielded, more protected. You can use, for example, the design techniques to shield the hardware. You can do redundancy and so on and so on. So I hope that does answer a little bit. But if I had to generalize it, I would say that we need a little bit more data to make a more informed decision. And this is where the challenge is in dynamic exit neural networks.
Okay, okay, thank you. All right. So we got one more questions from Sophia. All right. So the question is that does forward algorithm has any benefits over backpropagation for training dynamic neural networks specifically?
That is also a very good question. From the only network that we tested, it did, but we only tested it on one network. So, but I'm confident that, especially if you take this into consideration, that each layer is trained sufficiently that it can actually reach a very good decision. That's the objective of layer-wise training. Then definitely this particular approach, in addition to being beneficial in terms of the performance, the accuracy of the deep neural network, it's also beneficial to installing early exits. So yes.
Okay, thank you so much. So I think that that question was answered by Jackie. So the question is that will the recording be available at CEDA website? Of course, we will post it or on the CEDA website. All right. So I think the time is almost up. All right. So, Jackie, how about that? So I think probably we can conclude this talk, right? Okay. All right. So again, so Sal, thank you very much for sharing your research results and giving us such a wonderful talk, and also thank you all very much for attending this virtual DL talk. And in the following months, we will have two more VDL talks online. So specifically, one will be September, and the other will be finalized in this in I think in this month or next month. All right. So welcome to join us again. So see you all next time. So thank you all very much. Have a good day.
Thank you so much, Wiru. Thank you, everybody. I really appreciate you joining at this time. And if you have any questions, feel free to reach out to me via email. Most of you know me, so feel free.
Yeah, thank you so much, Sil. Okay, see you. Bye bye. Bye bye. Thank you for Jackie. Yeah, thank you, Jackie.
Bye bye, everybody.